What is the primary goal of using a support vector machine SVM algorithm in machine learning? A. To minimize the number of support vectors used to define the decision boundary. B. To maximize the margin between the decision boundary and the closest data points. C. To achieve the highest possible accuracy on the training data. D. All of the above. This statement is correct. Minimizing the number of support vectors reduces the model's complexity, leading to improved computational efficiency and better generalization. In simpler terms, fewer support vectors mean less data needs to be considered during prediction, making the model faster. Support vectors. This statement is correct. SVMs aim to find a decision boundary hyperplane that maximizes the margin between itself and the closest data points support vectors. This maximization leads to a more robust model, reducing the chance of overfitting and improving generalization to new data. Margin. This statement is correct. SVMs are designed to achieve high accuracy on both training and test data. While maximizing accuracy on training data is a goal, the primary focus is on generalization, ensuring good performance on unseen data. SVM quiz. This statement is correct. All the above statements are core objectives in SVM algorithms. Minimizing support vectors, maximizing margin, and achieving high accuracy on both training and test data are all interconnected and contribute to the effectiveness of SVM. Solution. D. All of the above. A hyperplane is a decision boundary in an SVM model that separates data points into different classes. It can be visualized as a line in 2D or a plane in 3D, and in higher dimensions, it becomes a complex geometric structure. In image classification, a hyperplane might be used to differentiate images of cats from images of dogs. In spam detection, it could separate emails into spam and not spam categories. Imagine you have two sets of data points representing cat and dog images in a 2D space. The hyperplane line is drawn in such a way that it separates the cat and dog data points with the maximum margin, allowing the SVM to accurately classify new images as either cats or dogs. The margin refers to the distance between the hyperplane and the closest data points support vectors from each class. A larger margin generally implies a more robust model, less prone to misclassification. In a medical diagnosis scenario, a larger margin between the hyperplane and the support vectors representing healthy and diseased patients would mean the model is more confident in classifying new patients accurately. Consider a 2D space where you want to classify patients based on two features: age and blood pressure. The margin would be the distance between the hyperplane lines separating healthy and diseased patients and the closest patients from each category. A larger margin indicates the model has greater confidence in its predictions. Support vectors are the data points closest to the hyperplane. They are critical in defining the decision boundary and influencing the model's prediction. They play a crucial role in generalization, as the model's performance is highly dependent on how well the support vectors are classified. In fraud detection, support vectors could be transactions that are very close to the boundary between fraudulent and legitimate transactions. These transactions help the model learn to distinguish between the two. In a spam detection model, support vectors might be emails that are very close to the boundary between spam and non-spam categories. They are crucial in defining the hyperplane that separates spam from legitimate emails.